Everybody, I wanted to go over colligative properties in this video. In this video specifically, we're going to talk about boiling point elevation. So with this colligative property, because we know that the solute, or by having a solution, the solute can change the vapor pressure. What that does is that will always cause an increase in the boiling point, because now we're decreasing the vapor pressure, and by decreasing the vapor pressure, that means that the boiling point is going to raise up. So boiling point elevation is a phenomenon caused by adding a solute into a solvent by creating a solution. And boiling point elevation, along with some other colligative properties, it's always dependent on the number of ions or the number of particles that are dissolved into the solution, or how many are produced by the dissolving process. So here's the formula for determining by how much, and that's what this is. This is the temperature change in the boiling point. And so in order to solve this, we would need the boiling point constant, and we need to calculate the molality, and then we need the Van 't Hoff factor. Now, I want to spend a little bit of time talking about this idea of the Van 't Hoff factor, which is this lowercase I, because the Van 't Hoff factor is usually somewhere around the number of resulting particles that are floating around in the solution that is created. So if you have something that is non-ionic but dissolves, like let's say sugar, okay, sugar when it dissolves has still just one molecule. So the Van 't Hoff factor for sugar is right around 1. When you have sodium chloride, when this goes into solution, you end up with a sodium ion and a chloride ion. So the Van 't Hoff factor is 2, because here now we have 2 particles, in this case 2 ions, that are produced. And so the boiling point elevation is dependent on the number of particles. So the funny thing is the more particles that are dissolved in the solution, I'm sorry, not the more particles. Well, okay, the more particles that are dissolved, yes, because of the molality, but also the more particles that the solution creates. So if you had something like CaCl2, that's a horrible CaCl2, okay, that produces 1 calcium ion, but it also produces 2 chloride ions. And so now we have a Van 't Hoff factor that's greater than that of sodium chloride. Just to be clear, the Van 't Hoff factor isn't exactly how many ions that are produced, but for what we're going to be using it for, this is a good approximation, okay? So I want to make sure that I am pretty clear about that. But we should probably do a sample problem where we're going to use this and what it ends up looking like. Okay, so we're going to talk about eugenol. I know that sounds like a weird compound name, but that's what it's called. So it says, what is the boiling point elevation of a solution containing, so it's 0.144 grams of eugenol. It's dissolved in 10 grams of benzene. Now, in order to do this problem, we're going to do the change in boiling point. T is temperature, capital T is temperature, but when you put that sub BP there, that's the boiling point. So the change in boiling point is equal to KBP, that constant, times the molality, and I'll use a script M there, okay, and then times the Van 't Hoff factor. And we're going to have to at the very least look this up. Okay. Now the Van Hoff factor here, I, for this compound, this is not an ionic compound. This is some of the stuff that we can identify, but so that makes this problem easier. This is not an ionic compound. This is definitely a molecular compound, a covalently bound compound. It's C's, H's, and O's, which are all nonmetals. And so that means your Van Hoff factor in here is 1. Okay, so we have to assume that this guy here doesn't break apart into any ions, and there's no indication that it does. Okay, so from here we can now determine the molality. Molality equals moles solute over kilograms of solvent. Okay, so we have to make sure we convert this to moles, grams, moles. In order to convert it to moles, we need the molar mass. So I will call up my calculator here so that you can see what I am doing. Okay, so I'm going to do 10 times 12, that's for the carbon, plus 12 times 1 for the hydrogen, plus 2 times 16 for the oxygen. So the molar mass is 1 mole, 164. So we do 0.144 divided by 164, and we get an answer of that right there. So now moles of solute, 0.000878 moles over kilograms of solvent. Well, that's going to be 0.010 kilograms. Okay, so I'm going to take that and divide that by 0.01, and that's going to make that a little bit bigger. So the molality now is equal to 0.0878 molal. Okay, now a couple of things. Just keep in mind that I'd like to see those leading zeros in there. Okay, so now we need some space now that we're ready to plug and chug in here. Okay, so we have delta T boiling point, so that's the boiling point elevation, is equal to kBp. Now we need to look that up, and I went to my book and I found that the constant is plus 2.53. Okay. Sorry. Times the molality, 0.0878, times 1, the Van Hoff factor, 1. Okay. So now we do the math. We do that times 2.53, and then times 1. So the change in boiling point, delta TP, delta TBP equals 0.222 degrees Celsius. Okay, so that's the boiling point elevation. Benzene, which is the solvent here, has a normal boiling point of somewhere around 80.1 degrees. Okay, so the TBP of benzene equals 80.1 degrees Celsius. The new boiling point, and this is what I want to make sure that you understand, this calculates the change in the boiling point. So the new boiling point is higher, okay, is higher. If I can get my eraser out, because for some reason this is acting weird. Okay, the new boiling point is higher by 0.22 degrees. So the new boiling point, is equal to 80.322 degrees Celsius. Okay, and that's not a lot. And we wouldn't expect it to be a lot because it's not a lot of compound. Okay, so that is freezing or some boiling point elevation. Have a great day and see you later.